Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group. I will teach you Power System 1. In this video, I will discuss about performance of medium transmission line and I will discuss about two methods, condenser method and nominal T method. These topics are included in Module 5 of the subject Power System 1. Subject code is PC-EE-502. So let's start. Now, in previous video, I discussed about short transmission line. And in short transmission line calculation, the effects of line capacitance are neglected because such lines have smaller length and transmit power at a relatively low voltage, that is below 20 kV. However, as the length and voltage of the line increase, the capacitance gradually becomes of greater importance. Since medium transmission lines have sufficient length 50 to 150 km and usually operate at voltage greater than 20 kV, the effects of capacitance can be neglected. Therefore, in order to obtain reasonable accuracy in medium transmission line calculation, the capacitance must be taken into account. The capacitance is uniformly distributed over the entire length of the line. However, in order to make the calculation simple, the line capacitance is assumed to be lumped or concentrated in the form of capacitor shunted across the line at one or more points. Now, such treatment of localizing the capacitance gives reasonably accurate results. The most common use method for solution of medium transmission lines are condenser method, nominal T method and nominal pi method. In this video, I will discuss about condenser method and nominal T method. So let's start with condenser method. Now, in this method, the capacitance of the line is lumped or concentrated at the receiving or load end. Just you can show in this picture the capacitance of the line is lumped or concentrated at the receiving end or load end. Now, this method of localizing the capacitance at the load end is known as load end overestimates the effects of capacitance, and that's why it's called as condenser method. Now, one phase of the three-phase transmission lines shown in this picture, and where IR is the load current, R is the resistance per phase, XL is the inductance per phase, C is the capacitance per phase, cos phi R is the receiving end power factor, and Vs is the sending end voltage. Now, this is the phasor diagram of this circuit. Now, to make you understand better, VR is taken as reference axis, so we can write VR equals to VR plus J0. Now, Vs is the sending end voltage and VR is the receiving end voltage. So, VR is less than Vs, and VR is the voltage across this capacitance, so the voltage drop is across resistance R and inductive reactance XL. So, if we add VR and Is into Z, we get this Vs. So, VR plus Is equals to Vs, and also we can write Z is equals to R plus JXL. Okay. Now the current, the sending end current IS, the sending end current IS is divided into IC and IR, where IC is the current across the capacitance and IR is the current across the load. So IR lags behind the voltage VR and also IS lags behind the voltage VS as the power factor is lagging. So IR plus IC equals to IS. IS equals to IR plus IC. IR plus IC. IR plus IC equals to the resultant current IS. Sorry, IC. What is the value of IC? IC is the current across the capacitance. So we can write J into VR into C. VR into omega C. J omega C into VR, where VR is the voltage across the capacitance, and we can write this VR omega is equal to 2 pi f C. So this is the value of IC. Now IS equals to IR plus IC. Here IS equals to IR plus IC. Now put the value of IR plus J VR 2 pi FC. Now we can write the value of IR is IR minus phi R. Minus is for the lagging power factor. This can be written as IR cos phi R minus J sin phi R plus JVR 2 pi FC. Cos phi R. Now if I take common J term, then it is equal to VR 2 by FC minus IR into sin phi R. Now these are we just derived. The magnitude of the sending end voltage Vs is calculated as voltage regulation, percentage voltage regulation Vs minus VR by VR into 100. And percentage voltage transmission efficiency is equal to power delivered per phase by power delivered per phase plus losses per phase, that means power sent per phase, into 100. So power delivered is VRIR cos phi R and power delivered plus losses is VRIR cos phi R plus IS square into R into 100. This is the transmission efficiency. This is the transmission efficiency. Now, although condenser method for the solution of medium transmission line is simple to work out calculation, but it has some drawbacks. First, there is a considerable error in calculation because the distributed capacitance has been assumed to be lumped or concentrated. And second, in this method overestimates the effects of line capacitance. Here is a problem. A medium single phase transmission line 100 km long has the following constants: resistance 0.25 ohm, reactance 0.8 ohm, susceptance per kilometer 14 into 10 to the power minus 6 Siemens, receiving end voltage 66,000 volt. Assuming that the total capacitance of the line is localized at the receiving end alone, determine the sending end voltage, sending end current regulation, and sending end current, sending end voltage regulation and supply factor. The line is delivering 15,000 kilowatt power at 0.8 power factor lagging. Draw the phasor diagram to illustrate your calculation. So first it is given that resistance is 0.25 per kilometer and total length is 100 kilometers. So we calculate resistance for whole length of the line. So we multiplied it by 100, that is the total length of the line. So the total resistance is 25. Similarly, we calculate total reactance of the line and it is 0.8 into 100, that is 80 ohm. And susceptance is 14 into 10 to the power minus 6 into 100, that is 14 into 10 to the power minus 4 Siemens. Now it is already given that VR is 66,000. So from the above data and the given power, that is 15,000 kilowatt, we get the value of current. Here the kilowatt is converted into watt and this is already in voltage. So we calculate the load current, which is equal to 284 ampere. Cos phi r is 0.8. So from this value we can get the value of sin phi r. Now VR is equals to VR plus J0, as we are taking VR as the reference axis. So VR is equals to 66,000 and vector IR equals to IR into cos phi r minus J sin phi r, because here minus sign is for lagging power factor. So we put the value of IR, cos phi r and sin phi r. When we calculate vector IR is equals to 227 minus J 170. Now capacitive current is IC equals to, we already know the formula, J into Y, that is our susceptance, into VR. So this is equals to J92. Sending end current IS is equal to IR plus IC, that is equals to 227 minus J78, and magnitude of IS is 240 ampere. Just we putting the value of IR and IC, we get the value of IS, and the magnitude is determined from this value, which is equal to 240 ampere. Next, what is the voltage drop? Voltage drop is equals to IS into Z. We already know this formula. So put the expression for Z, that is R plus JXL, and putting the value of IS, R and XL, we get the value of ISZ is equal to 11915 plus J 16210. Now what is the value of sending end voltage? What is the expression? Vs is equal to VR plus IS into Z. So putting the value of VR, IS and Z, IS and Z is 11915 plus J 16210. We putting the value of VR, that is 66,000. We get the value of Vs, that is 77,915 plus J 16,210. From this expression we calculate the magnitude of Vs, which is equal to 79583 volt, and percentage regulation, that is Vs minus VR by VR into 100, which is equals to 20.58%. Now referring to expression 1, from this expression theta 1 is equal to tan inverse minus 78 by 227, and theta 2 is tan inverse 16210 by 77915. So theta 2 is equal to 11.50 degree. So theta is equals to theta 1 plus theta 2, that is 30.46. So supply or sending end power factor is cos phi s, that is equals to 0.86 lagging power factor. Next method is nominal T method. Now in this method the whole capacitance is assumed to be concentrated at the middle of the line, and the half of the line resistance and reactance are lumped on its either side. Now therefore in this arrangement the full charging current flows over the half of the line. One phase of the three-phase transmission line is shown as it is advantageous to work in phase instead of line-to-line values. Now here Vs is the sending end voltage, Vr is the receiving end voltage, Is is the sending end current, C is the current across the capacitance, V1 is the voltage across the capacitance, IR is the current across the load, and as the whole resistance and reactance are lumped either side of the capacitance, so here the value of total resistance R by 2 and XL by 2, here the value of resistance R by 2 and reactance XL by 2. Now in this case also we are taking VR as our reference axis, so VR is equal to VR plus J0, and in this case also the power factor is lagging, so load current IR equals to IR into cos phi R minus J sin phi R. To make you understand this diagram over PowerPoint presentation is quite difficult, so I will do board work to make you understand better. Now in the nominal T method, the resistance and inductive reactance are divided into two sections, and resistance is in one side of capacitance is R by 2, and other side is also R by 2, and similarly inductance of capacitance of either side is XL by 2. Now here we take VR as the reference axis, so we can write VR equals to VR plus J0, as VR is the reference axis. And what is V1? V1 is the voltage across the capacitance. So we can write V1 is the VR plus IR into Z by 2. Now put the value of VR. IR is IR cos phi R minus J IR sin phi R, and Z, that is R plus JXL. This is the value of capacitance across voltage across the capacitance. Next, IC is the capacitive current. IC equals to J omega C V1, because the voltage across the capacitance is V1, so omega is 2 pi F C into V1. Next, Is equals to IR plus IC. From the circuit and also from the phasor diagram, IR plus IC equals to Ix. And sending end voltage Vs equals to V1 plus Is Z by 2. This is equals to V1 plus Is into R by 2 plus JXL by 2. Already I have discussed that V1 equals to VR plus IR into Z by 2, and putting the value of IR and Z, we get this expression of V1. IC is equal to J omega C into V1, which is equal to J. We put the value of omega, that is 2 pi F C into V1, and Is equals to IR plus IC, and Vs equals to V1 plus Is into Z by 2. So here is a problem. A three-phase 50 Hz over a transmission line 100 km long has the following data: resistance per kilometer per phase 0.1, inductive reactance per kilometer per phase 0.2 ohm, capacitive susceptance per kilometer per phase 0.04 into 10 to the minus 4 Siemens, Determine the sending end current, sending end voltage, sending end power factor, transmission efficiency when supplying a load of 10,000 kilowatt at 66 kV, power factor 0.8 lagging. Now we use nominal T method. So this is the circuit diagram of nominal T, and this is the phasor diagram of nominal T method. Then total resistance is multiplied by resistance per kilometer by the total length of the line. So we get the total resistance, that is equal to 0.1 into 100. So 10 ohm is the total resistance per phase of the line. And similarly we get the total inductive reactance, that is 0.2 into 100, 20 ohm total reactance per phase, and capacitive susceptance is equal to 0.04 into 10 to the minus 4 into 100, that is equal to 4 into 10 to the minus 4 Siemens. Receiving end voltage per phase equals to VR equals to 66,000 by root 3, this is equal to 38105 volt, and load current IR equals to power by root 3 into voltage into power factor. So by putting the value of power, that is 10,000 kilowatt, voltage and power factor, and converted the power into watt and voltage into volt, we get the final value of the current is 109 ampere. So this is the receiving end current or the load current. And cos phi r is 0.8. So from the formula sin square theta plus cos square theta equals to 1, we get the value of sin phi r is 0.6. Now impedance per phase is equal to R plus J XL. Put the value of R and XL, we get the value of Z. Now taking receiving end voltage as reference, so VR, we can write VR is equal to VR plus J0. So this is equal to 38,105 volt, and IR equals to IR into cos phi r minus J sin phi r. So put the value of cos phi r, sin phi r and IR, we ultimately get the value of load current, that is 87.2 minus J 65.4. And V1 is equals to, we know the formula already, we derived this formula already, VR plus IR into Z by 2. Putting the value of VR, IR, Z, we get the final value of voltage across the capacitance, that is equal to 39,195 plus J 545. Next, the expression of charging current is equal to J into susceptance into V1, that is voltage across the capacitance. And we put the value of susceptance and V1, we finally get the value of charging current, that is equal to minus 0.218 plus J 15.6. Now sending end current is equals to IS equals to IR plus IC, and put the value of IR and IC, we get the ultimate value, that is equal to 100 angle minus 29 degree 47 minute ampere. So sending end current, magnitude of sending end current is 100 ampere. Next, sending end voltage, we already derived this formula, and putting the value of V1, IS and Z, we get the value of Vs, that is 40145 magnitude and angle 1 degree 40 minute volt. Line value of sending end voltage is equal to phase value into phase voltage into root 3. So what is the magnitude of phase voltage? 40145 into root 3. So this is equal to 69.533 kV. This is the sending end voltage. Now study this phasor diagram. Here theta 1 is the angle between VR and Vs, and theta 2 is the angle between VR and IS. So by adding theta 1 and theta 2, we get this sending end, we get theta S. So theta 1 is the angle between VR and VH, which is equal to 1 degree 40 minute, and theta 2 is the angle between VR and IS, and this is equals to 29 degree 47 minute. Now by just add two value which is equal to 31 degree 27 minute. As theta is equals to theta 1 plus theta 2, so we can neglect this minus sign, this is just for the direction. Now theta is equals to 31 degree 27 minutes. So sending end power factor is equal to cos theta is equal to cos 31 degree 27 minute, which is equals to 0.853 lakh. Sending end power is equal to 3 into Vs Is cos phi s. By putting the value of Vs Is and cos phi s, we get the value sending end power 10273.105 kilowatt. And power delivered is already given in the question, that is 10,000 kilowatt. So transmission efficiency is output power, that is power delivered, by input power, that is sending end power, into 100. And putting the value of power delivered and sending power, we get the value of transmission efficiency 97.34%. Here is another problem. A 3-phase 50 Hz transmission line 100 km long delivers 20 megawatt at 0.9 power factor lagging and at 110 kV. The resistance and reactance of the line per phase per kilometer are 0.2 ohm and 0.4 ohm respectively, while the capacitance admittance is 2.5 to 10 to the power minus 6 Siemens per kilometer per phase. Calculate the current voltage at the sending end transmission efficiency. So by the so total resistance is equal to resistance per kilometer into total length, that is equal to 20, and similarly we calculate the reactance for whole length of the line, which is equal to 0.4 into total length, that is 100 kilometer, this is equal to 40 ohm. Similarly we calculate susceptance, this is equal to 2.5 into 10 to the power minus 4 Siemens. Now phase impedance Z is equal to 20 plus J40. Now receiving end power is given 110 into 110 kV. So we first convert it to volt and divided by root. Receiving end voltage per phase, that is equal to 63,508 volt. Load current is equals to power by root 3 VR into cos theta r. So already P is given, power is given, receiving end voltage is given, and power factor is given. From this we calculate the load current, which is equal to 116.6 ampere. Now from as cos phi r is given 0.9, so we can easily calculate sin phi r, which is equal to 0.435. Taking receiving end voltage as the reference axis, so we can write VR equals to VR plus J0, and put the value of VR. IR equals to, as the power factor is lagging, so we can write IR into cos phi r minus J sin phi r, minus is for lagging power factor. Put the value of IR cos phi r sin phi r, we get the load current 105 minus J 50.7. Voltage across V1 is equal to VR plus IR into Z by 2. We already derived this expression. By put the value of VR, IR and Z, we calculate the value of V1, which is equal to 65572 plus J 1593. Charging current IC equals to J into susceptance into V1. Put the value of susceptance and V1, the ultimate value of the charging current is minus 0.4 plus J 16.4. Sending end current IS equal to IR plus IC. Put the value of IR and IC, we get the value of IS, which is equal to 104.6 minus J 34.3. Now convert this rectangular form into the polar form, and the magnitude is 110 and the angle is minus 18 degree 9 minute ampere. So magnitude is 110 ampere. Now we now we calculate the sending end voltage. Vs is equal to V1 plus Is into Z by 2. Put the value of V1, Is and Z. We get the final value of Vs, which is equals to 67304 plus J 3342. Now from this rectangular expression we can calculate the magnitude of the sending end voltage, which is equals to 67387 volt, and convert it into the line voltage. We multiply it by root 3. So final line voltage is 116.717 kilovolt. Now we calculate the transmission efficiency. the power delivered is given, so we calculate the sent power is equal to power delivered plus losses. We calculate the total line losses. For 3 phase, total line losses is equal to 3 into Ia square by R by 2 plus 3 IR square into R by 2, because resistance is divided into two because resistance is divided in two sections. So if in first the current flowing through resistance is Is, and in the second half the current flowing through the resistance R by 2 is IR. So by put the value of ISR and IR, we get the final value of total loss is 0.770 megawatt. Now from the output power delivered and input power sent plus losses into 100, we get the percentage transmission efficiency, which is equal to 96.29%. That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.